On page 1 of the sample test, these questions are all in randomized order, so there's no real rhyme or reason to them. So I'll just do solutions to each one and see how they go. Here I'm solving an equation. The variable is in the exponent. Right? The variable is up in here. So we would consider this an exponential equation. And our strategy for solving an exponential equation is first to isolate the exponential part. So in order to get this thing that I circled to be by itself on both sides, first I need to subtract 3 from both sides, giving me 4 times the thing that I circled. I won't even bother writing down what it is yet. On this side I'll have 39 minus 3, which is 36. And then I'm going to divide both sides by 4, or multiply both sides by 1/4. On the left side, that's going to make this stuff go away, and all that I'll have left is the exponential parts, and I'll go ahead and write it down. It's 3 to the 4x plus 3. And on the right side, I have 36 times 1/4, which is 9. In this case, this is one of the easier problems in that I can make both sides be written as exponents with the same base, exponentials with the same base. So because 9 is really 3 squared, I can rewrite it like this. And we know that since the exponential functions are 1 to 1, that if you have an equation with the same base, then that means the exponents have to be the same. So the exponent 4x plus 3 must be equal to 2. And so the x here will be negative 1/4 if I solve that for x. So subtract 3 from both sides, divide both sides by 4. This is the same thing because the left-hand side is an exponential expression with base e, and the right-hand side could be written, instead of 1 over e squared, could be written as e to the minus 2. Now I have an equation where I have the same base on both sides, so it doesn't matter what the base is. If I have the same base on both sides of the equation, then that means that the exponents have to be the same. And if I subtract 3 from both sides and divide by 5, I'll get x equals negative 1. This one does not look like that. I have a right-hand side here that does not look like a power of e, so I'm going to have to use logarithms to solve this. And what we found out was that any exponential equation can be rewritten as a log equation with the same base. A base e in the exponential equation would correspond to the ln function for log function. Remember, ln is just a shorthand for log base e. So I know this is going to be a logarithmic equation with the same base, and the only difference is in the exponential equation, the input was 3x plus 4, so in the log equation, the output should be 3x plus 4. And in the exponential equation, 22 was the output, so in the log equation, 22 should be the input. So all that's happened is the 22 and the 3x plus 4 power switch places, and instead of a base e exponential equation, I have a base e logarithmic equation. So I don't know what natural log of 22 is. Certainly it's something I can put on my calculator, but if I want the exact value, then I'll just subtract 4 from both sides. Just leave this alone. And then divide both sides by 3. And so my final answer here will be natural log of 22 minus 4, all divided by 3. So that's the exact answer. If you put it in your calculator, you can get that to 6 or 7 decimal places, but really the exact answer is the best answer. And number 4, this is, again, this is, we can rewrite this in terms of exponentials if we want to understand it better. If I have the log of 1/25 equals something, that's equivalent to the exponential equation with a base of 5. 5 to the something equals 1 over 25, which doesn't really seem helpful, except that 25 is a power of 5. So I have 5 to the mystery power is equal to 5 to the negative 2. So 1 over 25 is really 1 over 5 squared. And just like in the second problem, 1 over 5 squared is really 5 to the negative 2. So if 5 to the mystery number equals 5 to the negative 2, that means the mystery number is negative 2. And that's what I was trying to find. I'm trying to find what that question mark is. So the answer here is negative 2. This is simply reading a graph, so there should be nothing different about this versus other problems. This is an exponential function, we can tell, because it has a horizontal asymptote going down like that. So we know this is, mostly because it's in this chapter, we know this is probably going to be some simple exponential equation. But the problem just says f of negative 1, which means that I'm looking for the x-coordinate being negative 1, and then the answer is the y-coordinate for that. So if x is negative 1, I'm writing here, the y-coordinate looks like it's 2. So a little hard to tell on this screen, but on the printout you can see it a little bit better. But when x is negative 1, y is 2. So that's the answer. Number 6 looks like the ones on the other page, as long as I know that 64 really is a power of 2. So first thing I would do is rewrite this as a power of 2. I can tell that I want that to happen because I have powers of 2 and powers of 2. And so if you know that you think that could be a power of 2, then just start multiplying 2's together and see if you get that. And the answer is yeah, you will when you get to 6 of them. So 2 times 2 times 2, 6 times is 64. So get rid of that so it doesn't confuse me. So I have everything written as powers of 2. Now to use my property where I get to just ignore the bases, I first need this left-hand side to be a single power of 2. Right now it's an expression involving powers of 2. So I use my laws of exponents, the law that says if you divide one power of 2 by another power of 2, then the powers should be subtracted. So what you see here is my new power is the power in the numerator minus the power in the denominator. So this is really the equation that I have. And of course 4x minus 2 minus 4 is really 2 to the 4x minus 6. So 2 to the 4x minus 6 equals 2 to the 6th. Therefore, I can ignore the bases and just see when the exponents are equal. Oops, that's a 6. Equals 6. So add 6 to both sides, divide both sides by 4, and we'll find that x here is 3. Number 7, again, I have my x is stuck inside of a logarithm, and so when my x is stuck in an exponential or a logarithm, I'm just going to use my equivalence and change it into the other kind of equation. So a logarithmic equation is equivalent to an exponential equation. The base will be 8. Right? The base 8 was 8 for a log, so the base will be 8 for the exponential. The only difference is, instead of x plus 7 being the input, x plus 7 will be the output here. And instead of x plus 7, instead of 5 being the output of the log expression, 5 will be the input to the exponential expression. So I have 8 to the 5th equals x plus 7. Now 8 to the 5th is a large number, so I'm going to do that on my calculator. 8 to the 5th power is 32,768. Equal to x plus 7. So 7. By subtracting 7 from both sides, I'll have that x is 32,761. The problem involving interest rate is really not much of a word problem. It's not really getting you to set anything up. It just wants us to use the formula. So this formula takes time as the inputs. So if the input is how much time, how many years of investment, and the output is how many dollars you have. So when the question says, what is the amount, that's asking for the output when the input is 3. Input is number of years it's invested. So this question is really just asking what is A of 3. And so A of 3 is 3,547 times e to the 0.01 times 3. And again, I would have to use a calculator to do that. And I get my answer 3,655.02. So it wants the answer to the nearest cent. So $3,655.02. In number 9, we have a logarithmic equation, and so we learned that we could rewrite that as an exponential equation, but in this case, notice that on both sides, we have log with the same base, and so the same thing's going to happen here that happens with the exponential equations, because the log equation also is 1-to-1. So if both sides are written as log base 5, then that means that the only way that can be equal is if the inside here is equal. So if we have log equals log and the bases are the same, then we can ignore the logs and just see what the arguments are the same. And so x should be -9, I believe, for that to work. Don't forget to check. This is important with log equations because they have a problem in the domain. If you check, then the equation will say log base 5 of -63 is equal to the log base 5 of -63, and that's a problem because there is no such thing as the log of -63. So this actually doesn't work. It would be true if the log of -63 makes sense, but it doesn't, and so we can cross that out and say this particular problem has no solution. So just like when we had square roots in equations, it's important when we have logs in equations that we check our answer at the end. And then finally, approximating the log basics of 10. This is just a matter of knowing the base conversion rule. It's the same thing as natural log of 10 over natural log of 6, which is to 3 decimal places would be 1.285. And if you're not sure, you can check, because it should be the case that 6 to the, remember this is a base 6 log, so the base 6 exponential, and again I'm only rounding this to 3 decimal places, so it's not going to be exact, but it should be that if I do 6 to that power, I'll just write down what I actually get when I use the truncated thing there, 1.285. I get 9.998, so the point is that it should be approximately 10.